Welcome back to the second part of this chapter on perfectly secret encryption. So last time we introduced Shannon's definition of perfect secrecy, which requires that ciphertexts are independent of the plaintexts they encrypt in a probabilistic sense. This definition, however, is not easy to work with when designing larger protocols. Also, it doesn't immediately generalize to weaker notions of security that allow for more efficient schemes. Another approach could be, in the context of historic ciphers, we have seen distinguishing attacks, where the adversary knows that a ciphertext encrypts one out of two messages and it has to find out which one it is. Is this maybe a minimal attack goal? So let's look at a security definition inspired by this. Here's our second attempt at defining perfect secrecy. In this definition, we say that an encryption scheme is perfectly secret if it holds for all pairs of messages M prime and all ciphertext C that the probability that encryption of M leads to the ciphertext C is identical to the probability that encryption of the message M prime leads to the ciphertext C, where of course, again, the key K is chosen by the keygen algorithm. What this says is that the distribution of ciphertexts is the same for any possible message. As before, in these probabilities, the probability is taken over the random choice of the keygen algorithm, that is the random choice of the key K, and the coins of the encryption algorithm ENC. Now, the definitions of perfect secrecy provided so far, namely definitions 1 and 2, are only concerned with the distributions of messages and ciphertexts. There is, however, no explicit mention of an adversary in these definitions. Now recall from lecture 1.3 that we want to study security notions against adversaries with different resources. So we'd like to have a definition which might easily generalize to resource-limited adversary. So what we're going to do now is we'll make the adversary explicit in a security definition. Okay, so we'll now define security via an experiment between an adversary and a challenger. This will turn out to be a very fruitful idea and will be the blueprint for many other definitions we'll see in this lecture. So let keygen, enc, and dec be an encryption scheme, and let A be a possibly unbounded, possibly randomized algorithm, and we'll call this algorithm the adversary. Now consider the following experiment. In this experiment, we have the adversary A and an algorithm or a machine which will talk to A called the challenger. So how does this experiment proceed? First, the algorithm A chooses two messages M0 and M1 and tells them to the challenger. Challenger takes these messages, generates a key K using the keygen algorithm. Now it chooses a uniformly random bit B and uses the encryption algorithm to encrypt the message MB using the key K. That is, if the bit B is 0, it will encrypt message M0. If the bit B is 1, it will encrypt message M1. And this ciphertext C we will call the challenge ciphertext. The bit B here will be called the challenge bit. So now the challenger returns the challenge ciphertext C star to the adversary, upon which the adversary has to make a guess B prime. If B prime is the same as B, the challenger will output 1, which denotes that the adversary wins. Otherwise, if B prime is not B, the adversary loses. So we call this the ciphertext indistinguishability experiment. And from now on, we let int a be a random variable which describes the output of the challenger at the end of this experiment. Okay, before I complete this security definition, let me remark that this definition really deserves the name security model, as it explicitly states what the adversary is allowed to do and what he gets to see. Namely, what is he allowed to do? He's allowed to choose the messages M0 and M1, and he sees the challenge ciphertext C star. Also, this definition states a well-defined attack goal, namely that there is a secret challenge bit B and the adversary has to guess it. Now, a real-world adversary might not be allowed, for instance, might not be allowed to choose the messages M0 and M1 himself, but we certainly err on the conservative side if we allow the adversary in our model to choose the messages, as this essentially doesn't make the adversary's task harder. So this definition is not complete yet, but now that we've defined this experiment between the challenger and adversary, we can provide the actual definition. We say an encryption scheme keygen encdec is perfectly secret if it holds for every adversary A, that is, for every possibly randomized algorithm A, and there's no computational bound on this adversary. So think of an adversary which might even have the power of solving undecidable problems. So if it holds for every adversary A, that the probability that this indistinguishability experiment returns 1 in the end is exactly 1/2, where the probability is now taken over all random choices of the experiment. That is, the random choices of A and the random choices of the challenger, who chooses this bit B, who generates the key K, and who computes an encryption. In the end, what this definition says is that whatever this adversary does in computing his guess B prime essentially amounts to random guessing. Whatever he does will not have a higher success probability than random guessing, because the success probability of 1/2 can always be achieved either by outputting a constant bit or just something random. Stated differently, no adversarial strategy to guess the bit B is better than random guessing. So this is a truly modern security definition, as it defines security by means of defining a successful attack. Or, stated differently, it defines security by what it means for a scheme to be insecure. You may have wondered already how the 3 definitions of perfect secrecy relate to one another. Are the modern ones better than the original one? Somewhat unsurprisingly, it turns out they're all equivalent. So while the statement of the theorem is simple and somewhat unsurprising, it will have a rather long and somewhat complex proof. But it is quite instructive to do this proof, as we will see many standard techniques that are used in many other proofs in this lecture. Thus, we will do this proof in full detail. In the future, though, I will not provide all proof details, as this would maybe be too time-consuming and not really instructive, as it would just repeat things or standard steps that you've already seen. So in the future, I will omit details which follow routinely, say by application of the base rule or the law of total probability, as you will see now in this proof. But in this proof, again, I will exercise this in full detail. So let's get started. And we will start with the conceptually simplest step, namely that definition 2 implies definition 1. So recall that definition 2 stated that for all messages M, M prime, and ciphertext C, we have probability that encryption, that the encryption of the message M gives you the ciphertext C is the same as the probability that encryption of the message M prime gives you the ciphertext C. So what this means is essentially that this probability here is the same for every message M. It sort of only depends on the ciphertext C. So we can say that if we define some value delta C, which only depends on C, this probability enc km equals C is the same for all messages M. So I maybe forgot to write up here that we're starting with definition 2 implies definition 1. Okay, now let's show that this implies the first definition. So what do we have in the first definition? We had some distribution of messages M. We need to show that it holds for all messages M and ciphertext C for all MC that the probability of M equals M conditioned on encryption of capital M equals C is the same as the unconditional probability or the prior probability of capital M being lowercase m. Okay, so how do we do this? The answer is, of course, base. This conditional probability here is somewhat unhandy because this encryption here, the ciphertext depends on M, but in turn the dependence of M or capital M on the ciphertext is unclear. So to compute this, let's turn this around via base rule. So writing this out, we have that probability M equals M given enc km equals C is the same as probability enc km equals C given M equals M times probability M equals M divided by probability enc km equals C. Now again, this one here is the one that should remain and the other stuff should cancel out. So let's first maybe look at this term here. I'm going to mark it in red. And second, we will look at that term. So in green, how do we compute this part? Well, let's just look at it. Probability enc km equals c, given that m equals m. Well, we know that when we condition on capital M being lowercase m, we can substitute capital M here for lowercase m. So this is the probability that enc k lowercase m equals c, given that m equals m. Now we also know that the random coins of enc and the key k are independent of the independently chosen of the message m. So this conditioning doesn't have an effect, because the left side here and this m equals m, or the ciphertext and message, are now independent. So this is just the probability that enc k comma m equals c. Oh, and for this we just derived, or this we just gave a name, namely up here we call this delta c. So we get that this is the same as our delta c. Okay, now we still have to compute the denominator. This is this term that I marked in red, namely probability that an encryption of M gives you a ciphertext C. Now, as is always the case, or as is almost always the case when we apply Bayes' rule, we compute this denominator using the law of total probability. And of course, that's what we're doing now. Same as all m prime in the support of this random variable capital M, such that probability enc k of our m prime equals c, conditioned on m equals m prime times probability of m equals m prime. So this term here we compute in exactly the same way as we compute the term that I marked green on the last slide. So we just exchanged m for m prime, but otherwise it's the same. This simplifies to probability encrypt m prime equals c, which also doesn't depend on m prime as we've seen above. This is just our term delta c. So now we can come back to computing or finishing the computation of what we were actually interested in, namely the probability m equals m conditioned on enc k of m equals c. Right, and we first computed this numerator in green that was delta c. The denominator also turns out to be delta c. Let me complete that up here. It's just m in support, m probability m equals m prime, and this is delta c. So the denominator also becomes delta c. Here you just note that these events equals m prime, they cover the entire sample space. Okay, let's go back down here. This was delta c by delta divided by delta c times probability m equals m, and that's just probability m equals m. All right, so what we've shown is that definition 2 implies definition 1. Okay, our second step will be showing that definition 3 implies definition 2. And we will show this via a contraposition. That is, we will assume that 2 does not hold and show that this implies that 3 does not hold. Okay, what does it mean for that 2 does not hold? Well, there are messages, or there exist messages M and M prime and a ciphertext C such that, well, probability that encrypting M gives you C is not the same as probability that encrypting M prime gives you C. Okay, so those two probabilities are bigger. Those two probabilities are different, so I can assume without loss of generality that one of them is bigger. Say the first one. The argument works the same way if the second one is bigger than the first one. So our strategy will be the following. We'll construct an adversary A such that, well, the probability that this adversary wins the indistinguishability experiment will be bigger than 1/2, which is a contradiction of the third property, right? Because there we require that for every adversary, this winning probability is exactly 1/2. So how does our adversary look? Let's write down both the adversary and the challenger. What does A do? Well, as messages M0 and M1, it will just use these M and M prime, whose existence was just given to us by assuming that property 2 is false. So it will use these M prime as his messages, and the challenger will do his thing, that is flip a bit, first generate a key, flip a bit, and then either encrypt M or M prime under this key and return the challenge ciphertext to the adversary. Now my adversary does the following once it gets this challenge ciphertext. If this challenge ciphertext is the same as this C up here, again, whose existence was just given to us, then it will guess B prime equals 0. Otherwise, if the challenge ciphertext is anything else, it will just choose B prime uniformly at random. Could also just always send 1 or whatnot, would work the same way. So otherwise it choose it, say we choose it as random, uniformly random, and send back this B prime. Okay, now we have our adversary, challenger. What's left to do for us is to compute the success probability of this adversary and show that it's greater than 1/2. So a first thing to observe is that the probability that the challenge ciphertext is equal to this ciphertext C, which was the condition for my adversary to output the guess B prime equals 0. So this event has a non-zero probability. Why is that the case? Well, we know that if the challenge bit B is 0, then we encrypt, or then the challenger encrypts the message M, right? Then the challenge ciphertext, this is then my challenged ciphertext C star for B equals 0. The probability that this is C is, by our assumption, greater than probability that encryption of K and prime equals C. Of course, this is greater equal 0. So we get that the challenge ciphertext C, or that the challenge ciphertext C occurs with a non-zero probability. Okay, so now let's compute the winning probability of our adversary A. We're interested in probability that this int A variable, which denotes the output of the challenger in the end, is 1. And now, once we have anything that's kind of a complex random variable that depends on a lot of other random variables, let's sort of take it apart. And the tool to take this apart is the law of total probability. And how do we do this? Well, my adversary does something interesting if the challenge ciphertext C star is C. If it's not if it's not equal to Z, he does something random. So the interesting case is if C star equals C. So let's use the law of total probability to write this as int A equals 1, conditioned on C star equals C, probability C star equals C, plus probability that int A equals 1, conditioned on C star not equal C. Excuse me. Times probability C star not equal C. So we already know that if the challenge ciphertext C star is not equal C, then my adversary just outputs a uniformly random bit. And the uniformly random bit B prime, and the probability that this B prime is the same as B is exactly 1/2. So in this case, my winning probability will be exactly 1/2. So what remains to show, or the slightly more difficult part, what we need to show, well, is that probability int A equals 1, conditioned C star equals C, that this is greater 1/2. If this is the case, it will follow directly that probability of that int a equals 1 is greater than 1/2 as desired. So, good. Let's jump to the next slide. Okay, let's look at this condition C equals C star equals C a little bit more in detail. Holds that, or if C equals C star equals C, it holds that this int variable, or the experiment outputs 1 if and only if b equals 0. Because in the case, if this event C star equals C happens, my adversary will always guess B prime equals 0. So he only wins, or the experiment only outputs 1 if also B equals 0. Right? Let's maybe annotate that here as whenever C star equals C, adversary A will guess B prime equals 0 by construction. It's just by the way I constructed this adversary. Okay. What that means is, under the condition C star equals C, or challenge ciphertext being C, the events int A equals 1 and B equals 0 are equivalent. Okay, so just as probabilities, it holds that probability int A equals 1 conditioned on C star equals C is the same as probability B equals 0 conditioned on C star equals C. And this term here already looks a lot friendlier as a term that involves this random variable int A. So what we will do now is we will compute probability B equals 0 conditioned on C star equals C, of course using Bayes' rule and the law of total probability. Okay, so let's jump for the next slide to do that. Okay, so let's do this. We want to compute probability B equals 0, conditioned on C star equals C. Just routine application of Bayes' rule gives us the same as probability C star equals C, condition on B equals 0, times probability B equals 0 divided by probability C star equals C. Okay, now the easiest term to compute is obviously this one here. We know that B is just a uniformly random bit, so it's 0 with probability 1/2 and 1 with probability 1/2. So the probability that B is 0 is exactly 1/2. So it remains to compute this term and, as always, the denominator. Okay, starting with the red one. How do we do this? Well, if the bit B is 0, then the challenger will always encrypt the message M. So in this case, the challenge ciphertext C star is an encryption of M. So it holds that probability C star equals C conditioned on B equals 0 is the same as probability that an encryption key K of the message M gives us the ciphertext C. Okay, so we computed this part. Next, let's compute the orange part. Well, and as is almost always the case in these denominators that arise after an application of Bayes' rule, we will use the law of total probability to do this. So probability C star equals C, challenge ciphertext being C, is okay. So over what should we apply the law of total probability? Well, up here we've already computed a term like this, conditioned on B equals 0. So let's apply the law of total probability over the outcomes of the challenge bit B. So this is the same as probability C star equals C conditioned on B equals 0 times probability B equals 0 plus probability C star equals C conditioned on B equals 1 times probability B equals 1. Okay, so what can we simplify here? Well, probability B equals 0, that's just 1/2. Same thing, B equals 1, B is chosen uniformly random, that's just 1/2 as well. Moreover, this probability, well, we've just computed it. That's probability of an encryption of M being C. And in the same way, let's maybe use a different color for that, maybe light blue. This is, sorry. In the case of B equals 1, the challenger encrypts the message M prime. So in this case, the challenge ciphertext is an encryption of M prime. Okay, so putting everything together, this is just 1/2 times probability enc K comma M equals C plus probability enc K M prime equals C. Okay, and now all we have to do is putting things back together. Let's do that on the next slide. So I get that probability B equals 0 conditioned on challenge ciphertext being C is probability NKM equals C times 1/2 divided by 1/2 times probability NKM equals C plus probability NKM prime equals C. Now, first thing, of course, this 1/2 cancels out, but I can further rewrite this by dividing both the numerator and denominator by this. I can write this as, oh, this is 1 divided by 1 plus probability NKM prime equals C divided by probability NKM equals C. So now this term here is smaller than 1. Well, why is that the case? Well, as probability by our assumption, and this is really now the only place where we use this, by our assumption from the beginning, NKM equals C is truly greater than probability NKM prime equals C. So overall, if this part here is smaller than 1, then it follows that this fraction here is greater than 1/2. And we're done with this part of the proof. Okay, so finally it remains to show the last implication, namely that definition 1 implies definition 3. So let's take ourselves any adversary A against the int experiment, as in definition 3. A be an adversary for the int experiment, as in definition 3. For now, assume that this adversary A is deterministic. That is, it doesn't make any random choices. So in definition 3 of perfect secrecy, I explicitly allowed that the adversary should be able to make random choices, but for the moment assume that it is a fully deterministic algorithm. So in particular, it means for instance, A always uses the same two messages M0 and M1. 0 and M1. Later, we will show how this generalizes to randomized adversaries A. Okay, so now we have an adversary A. Let's maybe draw the experiment here. A who always, no matter what, sends the same messages M0, M1 to the challenger. And the challenger, of course, first chooses his key. Next, it chooses a uniformly random bit B and encrypts the message MB. What I'm going to do now, and so forth, challenge ciphertext C star goes back. What I'm going to do now is I am defining a new random variable M, or I'm defining the random variable capital M, define the variable M to be just this message MB. So how does the probability distribution of this random variable M look? Well, we know that probability M equals M0 is just the same as probability B equals 0, right? Because the random variable M just deterministically depends on B. It is a function of B, which is 1/2. And of course, probability M equals M1 is the same as probability B equals 1, which is also 1/2. And for any message different from M0, M1, for M not in M0 or M1, we know that probability M equals M is 0. So if you want to write this distribution of our random variable M as a function graph, it would be, well, 1/2 for the messages M0 and M1, and 0, the distribution function would be 0 everywhere else. Okay. So we have that the challenge ciphertext C star is, I mean, just by the way how the challenger computes C star, is an encryption of MB. But now I just defined MB to be this random variable capital M, so C star is an encryption of M. And our idea is, our idea now will be, well, use what definition 1 tells us to show that C star is independent of M. Of M, and therefore of the challenge bit B. So if C star is independent of the bit B, that means that the adversary A doesn't learn any information about the bit B, and therefore whatever guess B prime he makes will be independent of the bit B. So let's make this formal. So as we just observed, M is just a function of bit. First, the events. Sorry, let's make this back. For beta in 0, 1, the events M equals M beta and B equals beta are equivalent. So if one event happens, if M equals M beta happens, then B equals beta, and if B equals beta happens, then M equals M beta. Okay, that is, we can now state that for all ciphertext C, it holds that probability B equals beta, conditioned on challenge ciphertext being C, is the same as, well, probability M equals M beta. I just said the events B equals beta and M equals M beta are equivalent, conditioned on C star equals C. And I can rewrite C star as an encryption of M. And now we have an expression at which we can throw definition 1. So by definition 1, we know this is exactly the same as probability M equals M beta. Again, as definition 1 says that ciphertext, the ciphertext C star and the message M are independent. And what is the probability M equals M beta? Well, for both beta equals 0 and beta equals 1, this is just 1/2 by construction. So recall that I said the algorithm A is deterministic. Which means that the guess B prime that A outputs is just a deterministic function of the challenge ciphertext C. Deterministic function of C star. Okay, now let's compute the success probability of our adversary A. We want to compute probability int A equals 1 and show that this is 1/2. Then we're done. But in order to do so, well, what is the, when does this event happen? Well, the challenger checks in the end if B prime is equals B, and then it outputs 1. So this event int A equals 1 is equivalent to the event B equals B prime of C star. And how can we go about computing this? Well, this B prime depends on C star, so let's use the law of total probability over all possible ciphertexts C. So we go over all C in C, and write this as the probability of B equals B prime of C star, conditioned on C star equals C times probability C star equals C. Okay, but we have just seen that this probability here is exactly 1/2. So for, or maybe let me rewind one step. We can rewrite this probability here. We can first substitute C star on the left side by C, as we're conditioning on C star equals C. And now this B prime of C star is, B prime of C is just a constant. So it's either 0 or 1. But we've just seen that for both this side here being 0 and 1, this probability here is exactly 1/2. So this becomes 1/2 times sum over all C, probability C star equals C. But of course here, these events C star equals C, they cover the entire sample space. So this is 1, which gives us that the probability that int A outputs 1 is exactly 1/2, which is what we have had to show. So now we know that every deterministic algorithm A has exactly success probability 1/2. But what about randomized algorithms A? Well, a randomized algorithm A takes as input additional random coins. Additional random coins. Coins are, they're chosen uniformly from 0, 1 to the L, where L is any length parameter that just depends on the adversary. So let's just write this randomized algorithm A, which for now, because we use it in the analysis, takes these coins as explicit input. So we write this as AR, or write AR, write as AR to make this explicit. Okay. So the idea is now, for every fixed string row in 0, 1 to the L, zero, 1 to the L, A of row is a deterministic algorithm. So instead of giving this algorithm A uniformly random coins as it expects, we could just take this algorithm, after all it's just an algorithm, and run it on any fixed input. So in particular, this means we've assumed that all the random choices that this algorithm A makes comes from this string R. That means our A row is a completely deterministic algorithm. That means, by what we've just shown, such a deterministic A has a winning probability in this int experiment of a row of exactly 1/2. That's what we've just shown. And now the rest follows by the magic of the law of total probability. Let's do that. Let's consider what happens if we give our adversary now the random coins it expects. So what's the probability that my randomized algorithm or randomized adversary A wins this experiment? Well, I'm just applying the law of total probability over all possible outcomes of this random choice R. So I'm just going over all row in 0, 1 to the L and look at the probability that, well, A of R equals 1 conditioned on R equals row times probability R equals row. So, and again, here we're conditioning on R equals row. So on the left side, I can just substitute R with row and get that this is the same as probability that int a row equals 1. And if this, as a row is now deterministic, as we just said, I know that this is exactly 1/2. Can just do the rest, write this as row in 0, sum of over all row in 0, 1 to the L, probability R equals row. Of course, these events R equals row cover the entire space, so this has probability, this probability is 1, which lets us conclude that also randomized algorithms have success probability exactly 1/2. So what we've done in this last proof is we've essentially used the law of total probability to de-randomize the analysis of the winning probability of a randomized algorithm A. And yes, this was a long proof, as I announced earlier, and now we're done with it. So let's come back to the question of key length and reusability of keys. In the last lecture, we've seen that that for the one-time pad, keys are as large as the message and can only be used once. And of course, we would either like to reuse keys or just have short or shorter keys. And the problem is, the question is this possible? Can we get perfectly secure encryption with short keys? The answer is no. In fact, this is the famous theorem of Shannon. If keygen enc is an encryption scheme with key space k, message space m, and ciphertext space c, it holds that if the scheme is perfectly secure, then the key space is larger, or at least as large, as the message space. In reverse, if I have a scheme where the key space is smaller than the message space, which means that I can encode the keys as shorter strings as the messages, then such a scheme cannot be perfectly secure. And this is exactly how we prove this. So let's assume that the key space is smaller than the message space. Our strategy will be show that there exists messages and a ciphertext, show there exist M, or let's call them M0, M1 and ciphertext C such that the probability of when I'm encrypting M0 that I get C is greater than 0, but the probability if I encrypt M1 to obtain Z is exactly 0. And this is, of course, this will be a contradiction against the second definition of perfect secrecy. This contradicts def 2 of perfect secrecy. Okay, so let's go for this. Let's show that these messages M0, M1, and such a ciphertext C exist. So how do we obtain the messages M0, M1, and the ciphertext C? Well, here's an idea. Start by fixing an arbitrary message M0. Furthermore, also a key K0. So M0 and K0, they're just fixed values, they're not random. And we set the ciphertext C to be just the encryption of M0 under, let's write it capital, under K0. So M0 is a fixed message, K0 a fixed key, not randomly chosen, like not generated by keygen, and we define C to be the encryption of M0 under K0. Now we ask the question, to which messages could this ciphertext C possibly decrypt? And towards this goal, we define the following set: S as the decryptions of the ciphertext C under a key K, where the key K goes over all possible keys in the key space. Now recall that we asked that the decryption algorithm is a deterministic algorithm, which means that for every key K here, for every candidate key K, there is only one message to which this ciphertext C decrypts to. What this means is that the set S can impossibly be bigger than the set K. Consequently, we have that the size of the set S is at most size of the set K of the key space, which by the assumption above is smaller than the message space. So we get that the size of S is smaller than the size of the message space, but we know that S is a subset of the message space, and we can conclude M without S is non-empty, which means there exists a message M1 in which is in M but not in S. There exists a message M1 in M, which is not an S. So now we claim there exists no key K, key K in K, such that C is an encryption under such a key K of the message M1. Now, to see that this is the case, assume there was such a key. So if there was such a K, then by correctness of the scheme, it holds. Well, what does correctness say? Correctness says that, well, let's try to decrypt this ciphertext C, but now we assumed that C is an encryption of M1. It would hold, or this would be decryption of encryption of M1, and correctness of an encryption scheme tells us that this expression is just M1. But that means we can decrypt C to M1, and that means M1 is in the set S. But this contradicts, of course, our the property of M1 that it is not in the set S, that it is in M without S. Okay, consequently, the statement follows. Which is, we found a ciphertext C, which is an encryption of M0, but under no key an encryption of M1. Okay, so now it's time to sum up this rather long lecture and this chapter. We've considered two alternative definitions for perfect secrecy, which approach the problem of defining security of a cipher from different angles. It turned out that all three definitions of perfect secrecy that we considered are equivalent. And finally, the need for large keys in the one-time pad is inherent if we want to achieve perfect secrecy. Now, this naturally leads to the question of which compromises we have to be willing to make in order to obtain efficient encryption schemes that have short and maybe reusable keys. That's all for now. Thanks.